Differential Equations, Section 3, Numerical Solutions. Video 1, the Standard Euler Method. Some differential equations do not have analytical solutions. In fact, those that you meet at A-level are a very small fraction of all the possible differential equations that could exist, and the vast majority of differential equations don't have a clever method that can be used to solve them analytically. In fact, they don't have analytical solutions at all. So, for example, something like dy by dx equals sine of xy, there is no clever method to solve this. There is no analytical solution. However, differential equations crop up in lots and lots of real-life applications, and so there's a necessity to be able to solve such things, even though they can't be solved analytically. And so what we do is we use numerical methods to approximate them. This is very similar how we use the trapezium rule in order to estimate the solution to integrals that can't be calculated analytically. In this topic then, we're going to start by looking at a simple method called the Euler method, and then we're going to modify this method later on in the topic to look at more sophisticated ways of approximating solutions. Now, the Euler method is based on the idea that although we can't solve the differential equation, we can at least use what we know about the gradient to approximate further points from a particular point that we're interested in. So here we are. Let's imagine that we had this differential equation dy by dx equals f of x, y. dy by dx is some function of x and y. And we know that it passes through a point x0 and y0. What we want to do then is we want to estimate a further point on the solution curve. We want to approximate where the curve might go next. So here's our point x0, y0. We know that at this point the gradient is given by f of x0, y0. So we consider a small step h along, and then we know that because the gradient is f of x0, y0, the y step upwards must be h times f of x0, y0. So to get our new point x1, y1, we take that x1 is x0 plus h, and then y1 is y0 plus h times f of x0, y0. What we're assuming here then is that for a small step along in x, the gradient is not going to vary very much from where it was. And our solution curve, which we don't actually know, the approximation to it is given by this new point x1, y1. So what we might do then is we might repeatedly apply the Euler method in order to give a sense of where the curve is going to go next. And just to show you how this works, what I've done here is I've plotted using the red line the analytical solution to a differential equation, but then the black line segments show what we would do for the Euler method. So starting from this point here where x equals 0.2, I've taken a step size h of 0.1, and then for each step I've used the gradient to make these little triangles here in order to approximate the curve. And to start off with, you can see that I'm pretty close to the actual solution line. But by the time I get to x equals 1, I've already got quite a gap between my approximation using the Euler method and the actual solution. So one thing that I could do is I could reduce the size of h. So instead of taking a step size of 0.1, I could take a smaller step size, and that would give me a better approximation. Now, the nice thing about this topic is because we have access to a spreadsheet, we can do lots and lots of iterations very, very quickly. And in the next video, we're going to see how to set a spreadsheet up in order to use the Euler method. In this video, you've learned the theoretical basis for the Euler method.